Ya, ok, listo. Buenos días a todos. Esto es la red LAFMAT, Red Latinoamericana de Física de Materia Condensada y Ciencia de Materiales. Red LAFMAT, conformada por varias universidades de Latinoamérica. Empezamos el año 2024 con la presencia de un nuevo palestrante. Es el doctor José de Jesús Velázquez-García. José de Jesús Velázquez-García, él es un mexicano que estudió en el Instituto Politécnico Nacional en México. Hizo su doctorado en la Universidad de Cambridge bajo la supervisión de la doctora Jackie Cole en el laboratorio Cavendish de la Universidad de Cambridge. Luego, José Velázquez-García se movió a Hamburgo a trabajar en el sincrotrón DESY en Alemania, donde actualmente trabaja. Su área, su expertise es estudios por sincrotrón, técnicas sincrotrónicas de Metallic Organic Frameworks, y es lo que va a hablar el día de hoy. También va a invitar a los estudiantes latinoamericanos e internacionales interesados en hacer doctorados o pasantías en el sincrotrón DESY de Alemania. Él tiene algunas plazas en su ramal y va a compartir con nosotros. Bien, welcome to everybody. This is the LAFMAT network, the Latin American Network on Matter Condensed Physics and Material Science. Is a network belonging a lot of universities. This is the first talk of the year with José Velázquez-García, who is a Mexican researcher who studied in the Instituto Politécnico Nacional in Mexico, then moved to the University of Cambridge, the Cavendish Laboratory in Cambridge. I studied his PhD studies in physics under the supervision of Professor Jackie Cole. Now he works in metallic organic frameworks in DESY synchrotron in Germany, Hamburg, Germany. Today he is also going to invite young researchers who want to study their doctoral studies in the synchrotron. Well, welcome, José de Jesús Velázquez-García, and you can present your talk now.
Okay. Thank you, Luis, for the kind presentation. So, as Luis said, I am a postdoc working in Germany. Probably I will share first my, sorry. Let's see. Can you see the presentation?
Yeah, you can see. Go ahead.
Okay. Then, as I said, I am a postdoc working in the Deutsches Elektronen-Synchrotron in Hamburg, Germany. And as Luis said, we have two PhD positions for students, especially in material science, physics, or chemistry, because this is mostly a multidisciplinary project. What we are asking is especially a robust understanding in crystallography and in organic chemistry, availability of traveling, because although some experiments can be done in the synchrotron here, most of the time we have to go to other synchrotrons to work, either Chicago, Italy, Diamond in the UK. That depends on the different characteristics of the project. And it would be it's optional, but it would be great if the person has some knowledge in Python or Gaussian and a bit of X-ray spectroscopy. That would be a great advantage. What we offer for these positions are that the standard salary for the PhD student is approximately, we think it's approximately 40,000 euros before taxes. We are not sure because that is, HR department and to be honest, we don't speak much with them. This place is too big, and talking with different departments sometimes it's a bit complicated. But it's the standard salary for a PhD student here, so it's a fair salary actually. And of course, you have access to different laboratories, and of course, travel expenses will be covered by the company. Well, the main objective of this presentation is actually to present the different projects and me personally am having at the moment. And it's one or two of these projects can be offered to one student and the other projects to other students. So first of all, I will talk about a bit of the crystallography. So most of the project involved either single crystal X-ray diffraction or photocrystallography. Most of the time, there is some photocrystallography involved in the project. So that is the main core of our research. I will talk a bit also first about a resume of what I spoke last time and a bit of the updates of what we have done or what I know so far. I will present some of the other projects that have more opportunity for the students, like metal silting in CU10, the project Charlie, the project Bob, and a bit of Celogel C8, which is most of the projects I have open. First of all, we'll speak about photocrystallography. A rough definition of this technique is a technique to determine structural changes in crystals after radiation with light. There are two types. It could be static for materials that after light irradiation can remain, the structural changes can remain there for, I don't know, several hours, days, months. Well, months could be the idea. And also the other one is time resolved photocrystallography, that is to study the structural changes or the structure of ephemeral species, the species that can live only for picoseconds, microseconds, milliseconds, who knows. One example of the static photocrystallography uses photoisomers. For example, my previous supervisor worked with the ruthenium sulfoxide isomers, which change the linking from one of the ligands toward the metal ion in this kind of metal complexes. And in the case of the time resolved photocrystallography, an example which we'll also treat here is spin crossover complexes, which the lifetime of the structural change only lives maximum a few milliseconds or microseconds. Well, first of all, we will talk a bit about the technique. So any crystallographic technique, practically, or single crystal technique, involves first a data collections, where you collect several images which later are processed in a computer. You obtain a model of the structure, and after that, you can actually obtain different, you can do an analysis of the different structural changes or the structure of the material per se at a defined time or at a defined condition. I like to think about crystallography, for example, it's like a photo shooting. So, for example, you go to a studio, you want to take photos of you from every angle, and at the end of the day, you can, after you take all those photos of every angle, you can process that information in a computer and create a three-dimensional model of yourself. In the case of time resolved photocrystallography, it's thinking like a photo shooting with a flash. So first the flash arrives, make you bright, perhaps you close your eyes, and then we have the model of you after the data processing. We have the model of you with the eyes closed because of the strong flash of the camera. So time resolved photocrystallography is something similar to that. First, instead of using a flash, we will have a laser pulse which excite the material, so the material in the single crystal, and after that, X-ray pulse will arrive and take and will be used to take the image of the of the pattern inside of the crystal, so the reciprocal image. And after taking many images, we can process all those images in the computer to obtain the model of the structure. And after we have the model, we can actually analyze the changes of the structure. So we can take that first in the dark before the laser excitation and after laser excitation, and then we can compare the structural changes before and after laser irradiation. And of course, the difference in time between the laser pulse and the X-ray pulse will give you more or less, so will give you the time at which, the difference in time between the laser and the X-ray pulse will give you the time of the picture. So the picture will be taken hundreds of picoseconds after laser irradiation, or could be taken a few nanoseconds, a few microseconds, or a few milliseconds after the light irradiation. And that will give you a molecular movie. So you will see the structural changes over time. And that would be used for modeling. So for modeling of the modeling of the photoexcited structure, or can be used for other type of dynamics changes. Well, I already talked about this. Okay, so for example, one of the typical things we use time resolved photocrystallography is for spin crossover complexes. Spin crossover complexes, some 3D4 to 3D7 metal complexes can switch between high spin and a low spin state configuration. This change can be made by temperature, pressure, or light. The importance of these complexes is because by changing from this electronic configuration, there is also changes in property. For example, there is a change in the magnetic properties, there is a change in the mechanical or electrical or optical properties. In our case, we are more interested, because of the photocrystallography technique, we are more interested in the light-induced changes. The light-induced changes in spin crossover complexes are very, very fast, passing from low spin to high spin, usually take 10 picoseconds. That is outside of the time resolution for time-resolved photocrystallography. However, the transition from low spin to high spin, there's some structural changes that can last hundreds of picoseconds, nanoseconds, milliseconds, or microseconds. So, as I said, the pass from low spin to high spin, the first thing that happens is a bond length expansion between the metal and the ligand surrounding the metal. Why? Because we pass for a bonding orbital to a non-bonding orbital, and therefore there is a change in the metal size. As I say, bond length expansion, the geometry of the pseudo-octahedral or octahedral can change to a more or less octahedral. And of course, because of the bond length expansion, there is an expansion in the volume of the coordination environment. This expansion can, of course, propagate to the molecular rearrangement. So the whole molecule will have some sort of rearrangement. There will be could be some change in the molecular interaction. So the pattern of the structure will change. And also there can be some changes in the microscopic regime. So it could be observable with a microscope, because the crystal could also deform. when we use a single pulse to excite the spin crossover crystal, there is a very multi-step out of equilibrium dynamics. So when a single pulse arrives to the single crystal of the spin crossover complexes, the first thing that will happen is the light will excite some ions, some metal ions from low spin to a high spin state. And that will create one of these changes we have mentioned. First of all, the bond length will increase. And if there is enough cooperativity on the material, that could pass to the molecular rearrangement, crystal packing, or the whole crystal, right? But usually the laser, the energy we introduce with the laser is higher than the necessary to produce this transition. So the excess of energy will also produce other changes. So there will be some crystal expansion because of the excess of energy. So there will start to be some heat or some propagation of the energy that will produce some elastic deformation in the crystal. And this elastic deformation will produce another transition from low spin to high spin. And this is what is called the elastic step, which usually takes place in the nanosecond regime. The first transition produced by the pure photons from low spin to high spin usually takes a few picoseconds, and this can last for hundreds of picoseconds until the nanosecond regime, when this elastic deformation due to the excess of energy will produce more transition from low spin to high spin. And after the crystal deforms because of the excess energy, there will be a global heating of the material. So the local temperature of the crystal will increase, usually a few, I don't know, 10 degrees I have seen most of the time. But this cool heating of the crystal will create a third step third step in the process, creating more transition from low spin to high spin. So it's a multi-step process where in each step there is an increase from low spin to high spin. And usually the elastic and the thermal steps are higher or surpass the pure photo-induced process. So we usually have more transition from low spin to high spin because of the heating or because of the elastic deformation of the material. And finally, we can say the last step is the recovery from the thermal step to the original ground state we started. In all these steps, there is usually a change. We can actually detect the change from the low spin to the high spin using photocrystallography because of the structural change, because of the bond length expansion. In monometallic, there is a curious thing. So it's usually, regardless of the step, you have only one change in the structural, only one structural change. However, in our case, we didn't analyze monometallic materials. We analyzed oligometallic materials. That is a cluster of a few metal ions strongly connected by the ligand. The ligand is a bit complicated. It's here observed in the slide, in the middle of the slide. And the type of the material we use is it has this great light shape. The first type of structure we have we have studied has 4 metal ions having a 2x2 structure. So where we have 2 metal ions in low spin and 2 metal ions in high spin. However, because of their dynamics and the structural configuration, usually when we excite the material, there is only one of these low spin materials pass to the high spin. In other words, we will have a structural chain from 2 low spin to high spin to 1 low spin, 3 high spin. We also have a similar structure where one of the high spin metal ion is missing. And finally, we have another grid-like structure when both high spin ions are missing. However, if you look to the metal, to the structure with only 2 low spins, you will see that there is nothing connecting actually the low spin ions. So in this case, this material, the so-called iron 2 grid, it's practically a dimer. It's a monometallic material, but arranged in a dimer configuration with 2 crystallographically independent metals. So when we actually photoexcite, we were expecting to behave more like a monometallic materials, which is quite interesting as we will see before. So we have the 3 systems, one totally connected, one which is connected only in an L shape, and one who are the 2 low spin ions are not connected. So we talked a bit about this in my last presentations. So the out of equilibrium dynamics in the totally connected grid, the so-called iron 4 grid, when we photoexcite, we have a structural response where we can track using photodifference map. Photodifference map is no more like the difference between the electron density between the excited state and the ground state. So creating this kind of maps where the red area indicates where the atom used to be, the metal, in this case, the metal ion used to be. And the green areas is where the electron density has shifted after light excitation. And as you can see here in the figure, I have put some pink arrows where it's showing more or less how the electron density is changing. For 2 of the ions, the electron density is moving up and down, while the other ones are moving out and inside of the plane. So it's moving like this. That occurs at 100 picoseconds, but after that, after 200 picoseconds, the movement changed, and this movement continued changing over time. In the first nanoseconds, this movement continued changing with some time. This is not observable usually in monometallic materials. In monometallic materials, after light radiation, there is only one change. So the direction is not changing over time. Here it is changing. The reason is because the metals are communicated. Once you excite or you pass one of these metals from low spin to a high spin, this triggers a movement, so it communicates to the other metals in the grid, and this passes information. When all the information is passed to the other metals, it receives a feedback, and this feedback is creating this constant rearrangement in the grid. And this stops until the elastic step, where the elastic step, the material just simply have some rearrangement towards the direction of the deformation of the grid, and then this stops until the thermal step, where practically it reached some sort of thermal equilibrium and the grid stayed there for most of the time, or stay there until it decays to the ground state. But this is most of the time. Well, this is our contribution to this type of science. We talk a bit about. We talked about it last time. What has changed since last time is that we have published what happens in the iron 3 grid. In the iron 3 grid, we observe something similar. There is some structural rearrangement over time. And of course, we also see that this structural rearrangement stops at 800 picoseconds because the to-induce step finish at 800 picoseconds, and after that, 1 nanoseconds, the elastic step also takes place. It's very similar to what happened in iron 4 grid. However, there is a substantial difference between the iron 3 and iron 4. Is that in iron 4 is visible the structural change and the spin crossover transition by temperature. The iron 3 grid, not. The iron 3 grid is not observable, the spin crossover by temperature. The reason is that there is solvent. The solvent trap, or the crystallizing solvent, silence the grids. So that's the reason with temperature is not observable, but with light it's observable, or barely observable, we would say. This work is a bit noisy compared to the other one. And yeah, the reason is we use different data collection strategy to obtain this work, and this data collection strategy is not as good as the other one. But because this material can decay faster with the laser, it's more sensitive, so we have to use a different data strategy. And we said that the iron 2 is a grid that is not connected. Practically, we have a monometallic material which is with two independent, crystallographically independent ions. So in this case, we should expect, and we observe, that the material over time, sorry, I put 200, but it's actually 200 and 500 picoseconds. So over time, this material remains the same. So after the light irradiation, the structural change is the same over time. It's not changing, it's not constantly changing like the iron 4 and like the iron 3. And as I say, the reason is because the metals are not connected. There is no communication between the metals. And there is another characteristic about this work. Contrary to the iron 3 and iron 4, which the light excitation was 390 nanometers, here we use twice that excitation, 790 nanometers. Why is that important? If we observe the UV spectra, we can see that, for example, iron 3 and iron 2 can absorb at 390 nanometers, but there is no absorption around 780. So because of that, we try to make sure that the material absorb light, or there is some sort of transition from low spin to high spin, both at 390 and 780 nanometers. So we use optical transient absorption in solution, of course, to track the low spin to high spin transition. When a spin crossover pass from low spin to high spin, there is a bleaching, especially around 400 nanometers, which is observable, for example, here in this slide. So if the material is having a transition at 390 and 780, we will be observing that in the optical transient absorption spectra, right? So, and we observe similar bleaching in both at 390 and 780. However, we have to use much higher laser excitation for at 700 nanometers. What is the reason of that? Well, also, the reason of that, or what we have expected, is because we are having a 2-photon absorption. In other words, we're having a spin crossover, because of 2-photon absorption. And this seems to be the first time we observe this phenomena in this kind of complexes. And we have registered by both optical transient absorption and by photocrystallography. One characteristic of this transition is observable by the differential absorption, or the change of the absorption with the pump fluency. In a normal absorption, the absorption with respect to the pump fluency is linear, but in a 2-photon absorption, it's quadratic. And we can observe this quadratic behavior when we photoexcite at 780 nanometers. What about the recovery? Well, we observe more or less that the absorption, the recovery after, well, in this case, 400 and 800 nanometers is the same. So when we excite in the crystallographic experiment 390 and 780, we expect also the same recovery from high spin to a low spin. And this is still a work. So while the iron 4 and iron 3 is projects that are complete, this 2-photon absorption in the iron 2 is still missing. There is some information I'm still working with. And if a student comes and I haven't finished, this will be a possible work for this coming student. There is also more work I still need to finish for the iron 4 grid. The iron 4 grid, all the grids has co-crystallizing solvent. However, there is something funny about the iron 4. So, for example, here, we can see the bond length expansion with temperature of the iron 4. So when we increase the temperature from 100 to 400, we can see a bond length expansion, not linear bond length expansion from one of the metals. We call it iron R, which is the one who is having the transition from low spin to high spin, while the iron B, which usually is always in the high spin, remains all the time in high spin. So there is no significant bond length expansion. The bond length expansion is linear and very small. So with co-crystallizing solvent, we see nothing really exciting, even if we go below 100K, which I didn't report in my first paper. However, when I carefully remove the solvent, I observe some small, some changes. Of course, when you remove the solvent, there is a higher structural change, so there is more transitions from low spin to high spin, or the transition occur at lower temperatures. And this of course occurs the same here. But also, if you see, for example, these gray and black triangles at low temperature below or around 100K, you see this reverse transition. So the material is passing again from low spin to a high spin transition, you may say, oh, well, you stop at around 80K. Yeah, recently, yeah, that's true. But recently, last October, I have some opportunity to go to the synchrotron here and make the experiment be below 800 Kelvin. And as you see, below 800 Kelvin, the revert process from low spin to high spin is taking place again. This, to me, to some extent, doesn't, well, it contradicts what we know about the spin crossover complexes. This because the transition, the thermal transition is from low spin to high spins occur when you increase the temperature. It's entropically driven, but here you are reducing the temperature and having a transition from low spin to high spin. This is an incomplete work. We have an idea of what it is happening, but we need more studies to do. In particular, some spectroscopy and some studies with magnetic susceptibility. So this would be another possible work for the students. So the same technique, photocrystallography, we have applied to metal-organic frameworks. In particular, metal-organic frameworks is just like a coordination polymers. So you mix a metal ion with some organic linker and you will form a 1D, 2D, or 3D structure, which have the possibility to have pores inside of the structure. The directionality that the ions gives to the ligands will make this material crystalline. So it's possible to study by crystallographic techniques. And if we use photocrystallography, we can try to track the structural changes after light irradiation. These materials are interesting because of the pores, because of the large surface area they have, and because it's very versatile. You can change the metal and the ligands in many different ways. So one of these famous materials is H-1, which are just composed by, or is made by by mixing copper nitrate with atrimesic acid, giving this kind of structure where here you will see the yellow are the sphere, where is the maximum sphere of the you can put in a pore. So here you can see at least two types of pores inside of the structure. And here in the last figure, you can see the metal cluster, which is the famous paddle wheel cluster of this type of of this material. When we photoxide this structure, I barely spoke last time about this. I saw some sort of structural change, and I put emphasis last time that, oh, I see some red electron, some red area around the metal, and some green about that. So I was expecting the material or the metal to move up. So the red is where it originally was, and it's now moving towards, so the metal is moving towards the green area. And here you can see the metal clusters at different angles. That was something I was thinking at the last time. However, I have done some more refinement and more obtained different structural maps, and now I think that this change may be false, may be caused by some spurious reflections obtained during the experimentation. However, there is something that always remains there, and this is green area close to the carbons or close to the oxygens. So regardless of how I treat the data, how many times I process the data, this seems to be a constant. And this green area next to the carbons may mean that the carbons are the ones who are changing after light irradiation. However, this could because, as I say, that you produce or you introduce more energy than necessary for photoinduced excitation. This may be because of the thermal effect. So this structural change we are seeing in the HCOS1 could be mostly driven by just thermal effects. And what could be this? Possibly a negative thermal expansion. So HCOS1 is very well known to have negative thermal expansion, and probably we are having the same when we just irradiate with light. Something, structural change similar to what we see at different temperatures. However, as I say, this needs more work, and this would be another possibility for an upcoming student. We try to use the photocrystallographic technique also for another MOF called CU10, which means Concordia University number 10. Usually it's made by a rare earth metal. This is the ligand. This is the asymmetric unit. And this is the overall structure along the Z-axis. And as you see, this material has very long spaces between the metal clusters. So these have even more larger pores than HCOS1. However, when we try to use the photocrystallographic technique, we had a problem. The material have X-ray induced transition. As you see, the materials have at 100K change from a yellow color to a red color. And that's occur at just some specific wavelengths of excitation with the X-ray, not at every excitation. And this occur only at some specific temperatures. If you irradiate the material at 250K, there is no change. And this change is metastable, so you can, after irradiation at 100K, this can live for several hours. I think the maximum I detect it was around 11 hours. And if you take this crystal after irradiation of, I don't know, 30 minutes, I think, and then put it outside of the cryo, you can still see the material. You can see still the changing color of the crystal. Even after you take it out of the cryo at 100K, the structural change, or sorry, the X-ray induced change can still be there. What is the most interesting part of this? So X-ray absorption is not something unusual. However, when we irradiate these crystals or these materials at wavelengths which are not in the edge, at the absorption edge of the carbon or the metal. So there is no real explanation why there is some X-ray induced change. Some people say, oh, it's probably the change you're showing is made by damage, radiation damage. If that were true, that would occur at all the wavelengths or all the wavelengths of radiation. However, this occurs only at some specific wavelengths, not at all of them. So, and it's metastable. It can live for several hours. So far we don't have much explanation. We have some. We have detected some structural change. Yeah, there is some change in the package, some change in the unit cell, some twinning. So, which means two phases are generating some change, some change unit cell, but we don't know the origin of these changes. So, this is another work for the possible coming students. Next is another project. Probably Luis know more about this project. It's Project Charlie. So in my time as a postdoc here, I have been working with some students who has just mix some ligands and some metals. Initially, they have mixed 2-methylimidazole, trimethyl acid, and cobalt, and they have produced some new metal-organic frameworks. One, we call it, this is a code name, so the code name is Charlie 2, which is a 2D network, and Charlie 4, which is a 3D network with a huge possibility to have channels. We have, to this material, we have checked that absorption. We have seen that in Charlie 2, it has some pores. However, the pore doesn't have possibility to be connected or to escape. So practically the pores are useless. So there is no possibility to encapsulate something really inside of the pore, or to introduce or take out something inside of the pore. And we see that in the absorption graph. So we have made some absorption measurements, and we don't see really important absorption on the material. And although we were expecting to have very large channels on Charlie 4, which is more like a 3D structure, we didn't observe, or we observed an even worse absorption in Charlie 4. The reason for that is because some of the ligand, in this case, some 2-methylimidazole, is trapped inside of the channels. So that impairs that blockades the channels to be useful. However, I came with the idea to introduce some inner molecule during the synthesis of Charlie 4 and practically trap that material inside of that. So as an initial molecule, I tried azobenzene. And as you can see that we can trap azobenzene inside of the molecule. Here you can see the azobenzene in the red circle, and you can see in yellow the trap 2-methylimidazole, which blockades the pore. So, but the surprising part is you can see the azobenzene. So practically you can have the structure of some trap molecules inside of the material. So this, of course, is not new, but that gives an application to this kind of MOF. So this new to Charlie 4. What is surprising is that when we introduce this material, this Charlie 4 loaded with azobenzene, when we introduce it in ethanol, some ethanol, we can actually see some slow release of the azobenzene. So we use normally UV spectra tracking how much, trying to see over time how much the azobenzene is being released in the alcohol. And if you see, it's a very slow release. It's not a sudden release that's usually observed, for example, in MOFs, in other MOFs, whose channels or pores are not blockaded, the release is usually sudden. Here the release is very slow, very gradual, which can give another application for other type of reactions. This work we expect to be published in the coming months, so there's not much at the moment to do with this one. However, we have other similar complexes, more than 23 complexes. Some of them are coordination polymers, some of them are small metal-organic complexes, and others are small organic subproducts. 2 of them we have already published, but there is still another. And all of these are possible works for the students. Next, and almost second last one, is Project Bob. So one of these materials, mixed ligand metal-organic framework, is not crystalline, it's polycrystalline, having some microscopic structures. This microscopic structure is a zero-gel. Zero-gel is no more than a solid material derived by a sol gel. We obtain that by slowly removing the liquid phase. These materials are very interesting. There are not many of these materials. These zero-gel usually have a porous structures, regardless of if the MOF is not porous. And some example of other zero-gels, recent zero-gel has been HCOS1, CFA, UIO66, CIF67. And practically it's almost, I don't know, it's 80% of the published zero-gels so far. So there is no more. However, this zero-gel is composed of two ligands. So it could be the first zero-gel, first mixed ligand zero-gel. However, we don't know so far the structure, and we know very little about the properties of this material. So this is another possible work for the coming students. Finally, I will talk a bit about the zero-gel CIF8. So the CIF8 is composed by zinc ions and 2-methylimidazole linker. Here you can see the overall structure with the yellow sphere, which show more or less the pore of the structure. CIF8 usually is obtained as a powder, most of the time nanopowder. However, it can be also obtained as a zero-gel, similar to the one obtained in the Project Bob. These zero-gel are large pieces with the microsite domain. Which is quite useful because powder is very difficult to process. So in real applications, powder is practically useless. So what happens with the CIF8, with practically every MOF which is obtained in the powder form, the MOF is compressed to form a pellet. However, this compression can produce a collapse of the pore, and then the quality of the material, the final material, is less than the crystalline form or the original form. When you create a zero-gel, you don't need any compression. You already have micro pieces which are quite manageable in the industry. So you don't need further processing. So you can directly use and conserve the pores or the properties. Sometimes the properties are even better in the zero-gel than in the powder. So this material has been used for photodegradation of dyes, especially methylene blue and rhodamine B. It has been reported for the powder a long time ago at different conditions, and it also has been reported the composite on powder form at different conditions. The zero-gel has been reported, but only at one condition. All the different pH, different concentration of the dyes, different concentration of the CIF8 has not been reported. And so the current students, the practicants who usually come every month to my lab, I usually give this kind of work and make a small publication where they can also participate. So there isn't, as I said, there is no full reported zero-gel properties of the material. So far, people think that the zero-gel form is less useful for the photogradation than the powder form, which is true, but it's less true at some specific concentration. That's what we have. So at some specific, pH, no, not concentration. There is also not reported zero-gel composites. No, not many zero-gel composites. So there is no much about the photogradation of some composites. So far, this is a work made by the practicants, but if when the students come, the PhD students come, they will have to lead these practicants, and so I can have some more time for my work, and the students can have some teaching experience with these practicants. So this is another possible work for these students. And with that, we come to an end. I just want to thank to all of the people who has been working with me here in my group from the Goethe University, which is the people who made the Iron Grid project. Some people who helped me with the optical transient absorption in the University of Hamburg, my collaborators in the Concordia University who made the CU10 material, and of course, thanks to Luis, which have helped me a lot with magnetic susceptibility and other things. Okay, with that, I thank you for attention and sorry for the messy presentation.
Okay, thank you very much, José Velázquez, for your nice talk. Well, first of all, to the public which is following this talk online, and you can leave some questions. You can type your questions on the link that you have followed this talk. Then we are going to transfer your questions to the speaker. A los que nos han estado siguiendo la charla del doctor José Velázquez-García, especialmente los estudiantes latinoamericanos, el profesor José Velázquez-García ha mencionado varios tópicos para financiamiento que tiene su laboratorio para hacer el doctorado en el sincrotrón DESY de Alemania. Entonces, ha mencionado varios tópicos con financiamiento, y si alguno de los estudiantes latinoamericanos que está siguiendo esta transmisión tiene alguna pregunta en estos momentos, puede dejarlo en las redes sociales donde ha seguido esta charla, y vamos a pasarles las preguntas al investigador. Well, now, the question from the panelists. First, we are going to start with a question from Professor Mario Reis from Brazil, who is in the Fluminense University, Federal Fluminense University. Mario Reis.
Yes, hello. Thanks for this opportunity. I have one question, mainly about spin crossover materials. Is it possible? I don't know if I understood really well about the technique. Is it possible to decouple the energy of the contributions of the materials, for example, the spin contributions and phonon contributions for the spin crossover materials, to decouple this kind of information?
So can you repeat the question? To decouple? I didn't hear very well.
To decouple the energy, for example, the spin energy and phonons energy.
Oh, well, so the photoinduced part, yeah, you mean the photoinduced part and the elastic part?
Yeah, I mean, considering it's a spectroscopy.
Oh, so in the spectroscopy is also visible. So I mentioned mostly about the structural changes, but in spectroscopy you will see the similar change. So no, not really, because once the elastic wave or the thermal part or any thermal effect is taking place, all the photoinduced part just practically disappears. So it's not really that is decoupled.
Okay. I have one more question, if I may. Is it possible to measure these materials under pressure, hydrostatic pressure?
Yeah, pressure is another type of induction from low spin to a high spin.
No, I mean, do you have this facility to measure under pressure?
We have the facility, but so far we don't have much interest on that, because we dedicate most towards the light, and what we try to use is to induce the changes without any wire, it's light. You can induce the structural changes. These materials are usually for optoelectronics, for example.
No, I
So-
see. I understand.
Mhm.
But do you have the facility? I mean,
There is some facility, but we need to bring our own cells. So if you are asking that, P24 is the beamline here in Germany where you can do this kind of studies.
okay. Luis, can I address one question?
Yeah, go ahead.
These samples that you presented, do you synthesize this by yourself, or is a collaboration with a
No.
chemistry group?
So the spin crossover is a collaboration with the Göttingen University. So that's another thing. So my professor is not from University of Hamburg, he's from Göttingen University. So if a student comes, also would be from associated to that university, to the Göttingen University. So this collaboration is a collaboration with another group in the Department of Chemistry in the Göttingen University with the professor Frank Meyer. They synthesize the complex and they do the initial characterization of the materials.
Okay. Thanks for your attention, for your talk.
Thank you.
Thank you very much, Professor Mario Reis from the Federal University of Fluminense in Brasil. Yeah. Bien, entonces continuamos nuevamente al público, los estudiantes que están siguiendo esta transmisión. Pueden dejar sus preguntas al doctor José Velázquez, que está ofreciendo financiamiento a los temas de doctorado en Metallic Frameworks en el Synchrotron DESY de Alemania. Yo sugiero que los estudiantes tuvieran alguna pregunta, sería genial, ¿sí? Y si José Velázquez puede dejar también su email luego o ponerlo ahí en la pantalla, sería genial. Well, let's continue with another question, another panelist. This is from the University of San Marcos, Universidad Nacional Mayor de San Marcos, Dr. Hugo Cabrera, Tinoco. Hugo.
Good morning. Good morning for everyone. Okay. Yes, I have good morning for everyone. Nice talk, Professor. I have one question. I think it's a curiosity to know about the material. About that material that increase the spin magnetization against versus the temperature. I hear that you say that you are researching, yet you don't have exactly the answer, but maybe to say some insights about that.
Sorry, can you repeat the question? I didn't hear the last part.
Maybe you can say some insights, some ideas about the answer of that, because it's curious because spin the magnetization increase against the temperature. Yes, you say in one material you of your talk.
But I have some problems to hear you. I hear some cuts. I don't know if everyone can hear.
I'm sorry.
Maybe
It's
can you use
the
Spanish?
internet.
Can you repeat the question, Luis? Both
Okay,
fine, but the thing is, I hear you some cut, like if
okay.
your sound is cut.
En
Sí,
español,
mi
Chugo.
pregunta es la siguiente. Sí, mi pregunta es la siguiente. Usted habló sobre unos materiales que, ¿no? Uno de los materiales que usted habló en la charla, ¿no? Me parece interesante que se incrementara la magnetización conforme aumentara la temperatura, ¿no? Entonces eso me pareció bien interesante porque, bueno, es algo que en principio podría ser, ¿no? Hasta contradictorio, ¿no? Pero bueno, quería saber, usted dijo que no estaba en investigación aún, pero si podría dar algún mayor detalle sobre ese tema, sí, sería interesante.
Well, los efectos magnéticos are totalmente entendidos. O sea, tú pasas de low spin to a high spin. So practically tienes una configuración electrónica diferente. Entonces pasas de un material diamagnético a paramagnético. O sea, esa no es muy interesante. Eso es prácticamente estudiado. Lo que es interesante es las razones por qué están cambiando. Por ejemplo, por la temperatura, en el caso de Iron 4, tú estás pasando de un low spin a high spin, enfriando. Eso no, es lo que no tiene sentido. Eso es lo que está contradiciendo la teoría. La teoría te dice que solo para incrementar la temperatura vas a pasar de low spin a high spin. Y sí lo obtenemos aquí, pero también al disminuir más la temperatura, estás obteniendo otra vez high spin. Y eso es lo que no se sabe. ¿Cuál es la pista? Si es lo que te estás preguntando, es estructural, no es molecular. O sea, la molécula sigue siendo lo mismo, pero es respecto al cristal. El cristal es el que está haciendo ese cambio. Por eso es que cuando nosotros quitamos el solvente, está pasando otra vez al, al high spin, de low spin to high spin. So, practically lo que estás haciendo es poniendo huecos dentro de la estructura. Pero necesitamos más confirmación de eso usando magnetic measurements, que es algo que nos está ayudando Luis. Y necesitamos un poco de espectroscopía, y eso también se hace en un síncrotron. Los experimentos están planeados para hacerse este año y veremos qué pasa.
Ok, profesor, muchas gracias por su respuesta.
Bien, muchas gracias, doctor Hugo Cabrera de la Universidad Nacional Mayor de San Marcos en Lima, Perú. Ahora nos movemos a Chile, a la Universidad de San Sebastián en Puerto Montt, Chile, con el profesor Felipe Mundaca. Felipe.
Hola Luis, hola José, ¿qué tal?
Hola.
Gracias por tu presentación. Me queda una pregunta con respecto a lo que nos mostraste sobre la degradación de ciertos tintes que mostraste como casi al final. Mi pregunta va en el sentido de los materiales que tú utilizas para degradar estos tintes. ¿Qué propiedades estás como intentando maximizar para degradar eficientemente estos tintes? Porque, bueno, al menos por lo que tengo entendido, uno trata de absorber la mayor cantidad de luz por estos materiales, ¿no? Entonces el backup tendría que tener un rango de 2 a 3 electron volt y, bueno, las constantes dieléctricas, ¿cierto? También es un parámetro importante y las más efectivas. Entonces mi pregunta es, si tú mides esas propiedades, o utilizas específicamente la más efectiva que se utiliza en radiación síncrotron.
No, en este caso no me estoy tratando de, ¿cómo diría? La mayoría de todas estas cosas ya está estudiada. Lo único que trato de hacer con estos practicantes es prácticamente es un low impact factor paper, let's say. Porque lo que pasa con el CIGEI, por ejemplo, con el zero gel, no es exactamente el MOF per se el que está haciendo la fotodegradación. Son los defectos que ocurren en el MOF. O sea, un MOF defectuoso es lo que está pasando. Cuando tú tienes un cristalito nanométrico, tienes un chorro de defectos. Cuando tú tienes un 0J no tienes el mismo, tienes un chorro de efectos, pero no es el mismo tipo de efectos. Y es lo que tratamos de ver, es lo que tratamos de observar. Y eso ya está, hasta cierto punto está publicado, pero no está publicado la extensión de estos defectos. No se sabe totalmente hasta qué punto pueden estos defectos ser mejores. Y lo que tampoco se sabe si introduciendo, en este caso, composites, o sea, introduciendo otro metal, aunque en la fase cristalina está estudiado, no está estudiado dentro del 0J. Sí, vamos a estudiar un poquito acerca de estos cambios electrónicos, posiblemente un poquito de los defectos, pero eso ya sería un poquito más después. Lo primero sería simplemente uno de aplicación, es un paper de aplicación, porque estos estudiantes no tienen ni licenciatura, están entre universidad y licenciatura.
Ya. Y mi otra pregunta es, con respecto a la susceptibilidad magnética que nos mencionaste, no me quedó claro, o sea, sé que es parte experimental, pero no sé si tú también lo has corroborado mediante, porque vi al principio que utilizabas, por ejemplo, Orca, o unos programas que utilizan cálculo
Ok.
GPT. No sé si también has intentado reproducir esa susceptibilidad magnética versus la temperatura utilizando
Sí,
cálculo abilitio con Monte Carlo, por ejemplo, porque para eso utilizamos Monte Carlo también.
la ventaja, por ejemplo, estudiar estos cambios con respecto, usando Orca, usando Gaussian, todas esas técnicas computacionales es bastante complicado. Y tuvimos la fortuna de que alguien ya lo había hecho antes que nosotros. Entonces, prácticamente utilizamos esos estudios para comparar lo que nosotros encontramos estructuralmente. Entonces,
Ya.
esa ha sido la fortuna, pero usualmente, por ejemplo, H-Cos1, necesitaremos, lo que ahora pienso es que los cambios estructurales que observamos son causados por thermal effects, o sea, exceso de energía. Pero si encontramos que es relacionado a un photo-induced change, tendríamos que utilizar también métodos computacionales para tratar de explicar qué transición electrónica está causando ese photo-induced change.
Ya, ok. Bueno, te dejo ahí nomás como datos si te interesa. Acá, bueno, hay otro colaborador acá también de la red, Sergio, que no pudo asistir hoy. Trabajamos en DFT, nosotros utilizamos Orca, utilizamos Gaussian y bueno, también Crystal 17 para simulación en sólido. De hecho, trabajamos también con el LastCast, perdón, el CMOS. No nos hemos metido en el caso de la susceptibilidad magnética, pero sabemos más o menos cómo trabajar eso, entonces,
Sí,
si te interesa en el futuro, podríamos ahí de pronto trabajar en algo.
sí, sí.
Sí,
Sí,
por
o sea,
ahí,
también estoy muy interesado en hacer colaboraciones, aunque debido a los cambios de reglas también que el gobierno alemán está implementando, necesito darle un poquito de tiempo, unos cuantos meses para saber qué es lo que realmente está pasando, porque lo que he escuchado ahorita son más como rumores, pero están haciendo las cosas un poquito más complicadas para hacer colaboraciones de este tipo.
bien. Bueno, esa
Pero
era
sí me
mi...
interesaría hacer, sí, o sea, si me pasa el contacto y una vez que sepa qué es lo que está pasando aquí, entonces sí,
Sí, claro.
podríamos
Bien,
definir algo.
claro. Gracias, José. Hasta
Gracias.
luego. Gracias, Luis.
Muchas gracias, doctor Felipe Mundaca, de la Universidad de San Sebastián en Puerto Montt, Chile. Bien, now let's move to Cambridge with Professor Stuart Holmes, who is in the University College of London as well. Stuart.
Thank you, Jose, for your talk. Very interesting. I have a couple of questions. I think Hugo asked the same question, I think. But in your low spin to high spin transition, you're kind of analyzing it through a structural change, do you anticipate Faraday rotation or Moke or some kind of dichroism measurement to confirm that the spin is changing, spin properties are changing?
Yeah.
I think he asked the same question, so apologies, you might get the same question
no.
twice.
No, it's not the same question.
Oh, okay. Okay.
Yeah. In this case, we wanted to use some sort of, but you have to understand. So we use solid state, right? So we use a crystal, but can be also used in solution. The difference in solution, you will not have cooperativity, right? Because cooperativity only occurs in the solid state. One molecule transmits the information to the other molecule. In solution, it's not the same because you have the solvent. So the solvent will absorb every structural change. So in the solid state, we haven't used any type of spectroscopy because of the difficulties to do that, especially optical spectroscopy. We try to do that, but we need to use reflective modes for that. And the reflective mode, I have never found anyone who's doing reflective mode in crystals. Most of the time they use transition mode. And these crystals are too black, so nothing passes the crystal. In solution, another group, practically 2 years ago, they published the results. So they show similar wavelength excitation and everything in solution. But that is only to study the photoinduced part. In solid state, you have the photoinduced, the elastic induced, and the thermal induced step. So it's a more complicated thing. So to confirm that, we can only use solution, not in the solid state.
Oh. Thank you. The other question I had was about the negative thermal expansion. Is that a metastable effect, or is that just a?
It's a structural thing. So
yeah,
the negative thermal expansion.
Yeah.
What happens? You have the pores, and when you cool down, the ligand bends, and because the ligand is bending like that, so practically the structure is just getting closer, and because it's a polymer, all the crystal is just contracting.
Yeah.
When you increase the temperature, instead of being bended, trying to cover the pore, it just expand. So it gets bigger. So that's the reason HCOT1 has a negative thermal expansion.
That's the interesting result. Thank you. That's a great talk. Thank you. Thank you very much. Thank you for answering the questions.
Yeah, thank you for asking.
Thank you very much, Professor Stuart Holmes from the University of Cambridge, University College London. Well, Rita Tenia es from the Universidad del Oriente en Venezuela. No sé si tiene alguna pregunta. Rita. Rita, tu micrófono. Rita. Ya, dice que no tiene preguntas y que disculpe por entrar tarde. Bueno, entonces vamos a Colombia. Si es que hay preguntas de la casi doctora ya Ximena Velázquez o del público, si es que hay también preguntas. Ximena, ¿nos dices, por favor?
Bueno, por un lado, muchísimas gracias. ¿Cómo está? Yo ya había conocido al doctor José. Muchas gracias por la charla, bastante interesante. Digamos, yo había conocido algo, pero no tan profundo. De mi parte no tengo preguntas. Si hay alguien por aquí que me pregunta de los estudiantes, si hay un chico en particular que dice, estoy estudiando maestría, ¿es necesario tener el grado de maestría o se puede directamente aplicar así? Esa es como la pregunta que...
Tendrías que terminarlo, sí.
Esa es la única pregunta que hay de los estudiantes. Pero en general, nada. Muchísimas gracias por la charla.
Gracias.
Ok, José, gracias, Ximena. José, respondiste, ¿cierto? Que sí es necesario que tenga su grado de maestría. Sí, perfecto. Y todos los documentos
debe tener todo. Además de que personalmente recomendaría que termine. Si ya está estudiando la maestría, mucho mejor que termine su grado.
Que
y
termine la
no-
maestría. Claro, ¿no?
Digo, eso es ya personal, pero
Son 40.000 euros. 40.000 euros
antes de
anuales.
impuestos. Debes de recordar que es antes de
Pues,
impuestos. Impuestos es
antes.
un buen en Alemania.
Si no, a
Así
mí
es
mismo me
que-
gustaría otra segunda. Está interesante, perfecto.
Pues manda tu
Eh,
aplicación, Luis.
Bueno, se podría hacer. Yo supongo que como estas charlas va a quedar grabada en nuestras redes, supongo que los estudiantes latinoamericanos van a estar interesados y ahí está tu correo electrónico, jose.velázquez@ds.de. Está con todo y tu teléfono también. Y
De la
vas a
oficina.
vas a estar seguramente recibiendo emails acerca de preguntas y etcétera para que se enrolen. Bien, entonces, José, para terminar, tienes nuevamente los micrófonos y la pantalla lista para que puedas, no sé, despedirte del público.
Ok. Bueno, solo agradecer a todos los que escucharon. La razón de darlo en inglés porque el trabajo va a ser hecho en inglés. Y pues espero que postulen. Hay mucho trabajo aquí y hasta ahorita no he recibido ninguna aplicación de algún latinoamericano y me gustaría, bueno, ver si alguien de Latinoamérica pudiera postular para acá. Ok, gracias por escuchar y eso es todo.
Bien, entonces a todos nuestros estudiantes latinoamericanos ya sabemos que hay plazas vacantes para hacer su doctorado en el DESY-Synchrotron de Alemania, bajo la supervisión del grupo del doctor de Jesús Velázquez-García. Puede contactarse su correo jose.velázquez@desi.de y también supongo que serán los puntos de siempre, que son su grado de maestría, ¿no? Haber terminado, conocimiento de inglés, y tiene financiamiento este laboratorio, que sin descontar impuestos, 40.000 euros anuales. Descontando impuestos yo le hago que sea alrededor de 30.000 euros anuales, alrededor, no lo sé, pero de cuánto estará los descuentos en Alemania. Pero es muy buena oportunidad para todos nuestros estudiantes latinoamericanos que recomiendo que lo aprovechen. Muchas gracias. Puedes dejar de compartir tu pantalla, José Velázquez. Ha sido un gran gusto tenerte nuevamente acá con nosotros. Por favor, abran sus cámaras todos los demás panelistas para decir hasta luego y sus micrófonos también. Your cameras and your microphones open, please, to say goodbye to José Velázquez. Your cameras, please. Sus micrófonos. Chao.
Wow, thank you.
I'm driving now. I
Dankeschön.
cannot turn on my camera. Bye bye.
Adiós, nos vemos. Chao.
Bye bye.
Gracias.
Gracias.
Bye bye.
Muchas gracias, José Velázquez. Ok, cortamos.